My name is Einar Lönn, and I work at the registry here at .se. I was asked to present some of our tools that we at the registry use to monitor DNS and DNSSEC. This presentation has been written by my colleague Niklas Rosell, but I think I know about everything in it, so you can just ask me questions if something is unclear. First of all, we have 4 different operators that we outsource the slaves to, and the slaves are the actual name servers that service the .se zone. And these are NetNode, Telia, Affilias, and VeriSign. And about the slave servers, we have roughly, at any one time, we have roughly 150 servers or instances of servers alive on the internet. And these are placed in a lot of different cities, as you can see there. And also we have these 4 different providers because that gives us a lot of less risks, since they have different routing procedures and everything. And we answer roughly 6,000 queries per second. 24 hours, of course. And locations geographically is roughly these. You see, we have mostly servers in Europe and Sweden, but we try to get servers in every part of the world because, and since we use Anycasts, it's especially good to have them placed at lots of different places around the world. We're trying to get South America, but it's very hard to get servers hosted there. And we have 3 important tools when we control the DNS and DNSSEC infrastructure. And these are our own developed DNSMON, which is basically a very nice user interface and some extra features based upon the Nagios backend. We also have my baby, DNSCheck, which is a delegation checking tool. I will speak about it more later. And we also have DNS2db, which is a packet dumping and packet analyzing tool. I also speak more about that. So, what do we monitor? We monitor availability, basically round trip times and if servers are alive. And we do this with a distributed probe network, because if we had a single monitoring server, we can't really prove that one of our slaves was down, because as you know, it's the internet, it's routing everything. So since we have this distributed probe network, we say that when a certain number of probes cannot reach, for example, one of our slave servers, then we can say that it's down. Because if half the internet can't reach it, it's basically down. We always monitor query load, and we do that by having limits. So if the load is 300% of normal, then we send an alert, and if it drops below 50% of normal, then we also send an alert. And zone correctness. We check that all the servers run the latest zone file, so a serial, very easy. If it replies correctly, and also we check for brokenness in the zone by going through the zone with some sample test zones, since they're always sorted alphabetically. And also DNSSEC, of course. We see signature expiration and that all the name servers handle large packets with the DNS null 0 and such. And also on our open source webpage, you can see there's the Nagios tool there that you can use to monitor the DNSSEC, and I'll show that later also, and some other stuff. So this is the user interface I spoke about, and it's basically very graphical, very nice front end to in the end Nagios data, Nagios alerts. And on this one you see the load hitting our servers. So you see it's almost around 6,000 queries per second here, and you have some spikes. Excuse me. Let's see if you can. Now it doesn't really show here, but the black border you can see, almost see here. They represent NX domain. So when the black line goes up and the load goes up quite a bit, it's almost always someone trying to do a dictionary attack. They're trying to find domain names that don't exist. The huge spikes when there's no black line are usually more interesting. That's sometimes can be a very noisy loop, or it can be a a reporting error, and then we have to fix it on our side. The quick status. Sorry. The quick status shows us what the probe tells us how it looks right now. So here it says A. We have all our slaves named A.ns.se, A to B to J.ns.se. So here all the probes have reported that A through J, all of them answer and seems to be okay. And these are the probes. Probe 10 here to 27. And they say okay when they have reported within the last, I think, 5 minutes. So they're constantly updating this list. So the DNSSEC Nagios controller module. This is open source. So yeah, if you go to opensource.is.s, you can see all our open source tools. It's very easy. If you know Nagios, then this is extremely easy to configure. Excuse me. It's just a simple Perl script that you give a zone, and you give the alert levels when it's two days left for the KSK, then it should be critical and so on. So it's very, very easy to use and implement. And here's how we use it in Nagios. You can see, yeah, not so pretty, but on our slave A, it says DNSSEC and it's okay. So it's passed. And this is also interesting since we're at the registry. Aha! Woo! Thank you. We at the registry. We don't manage these machines ourselves. We have a tech department that manages these machines, and they use. Now it's the same DNSSEC control, but they have a lower threshold on their controls. No, higher threshold. So they get an alert when they haven't rolled the KSK or something. So perhaps they get the alert 30 days before it expires, whilst we get the alert perhaps 10 days before it expires, which is very good because we have different systems that monitors basically the same thing. But since they should roll this key when they get the alert, so usually we never get any alerts. So it's a good separation of duties, and we have since we have lower threshold, we should never get any alerts. So it's a good thing to do if you have that company structure. Okay, to traffic analysis. DNS2db is a very, very promising, very cool tool. It's quite easy. It uses libpcap, something similar to TCP dump, to just dump DNS traffic hitting the slave servers, and then it uses another process to convert this PCAP files to SQLite databases. And this is, first of all, it scales extremely well since you have these different processes. You can make sure that you can always capture data at basically line speed, since you can do this conversion at a later date, or if you have multi-cores, you can always have a lot of these conversions going on at the same time and stuff like that. Also, since you store these packets in a database after you converted them, it's very easy to find anything in these databases. And of course, it's open source, so it's free for everyone to use, to play with. I think it's shown later on here. Yep. This is how it looks. The flashy front end. And here we see the nodes. So at this moment we had f.ns.se and g.ns.se using running DNS2db. And this is a passive collector in front of the slave. So even if the passive collector would die or something, it wouldn't affect any. The slave would never be affected, and that's how we recommend that people set it up, with a passive sniffer and a dedicated machine. You could run it on the same server, but that could be a problem, since if the server is under extreme load, then you're running out of CPU anyways. Then you shouldn't perhaps add this also. So we have a separate server and a passive sniffer. So it makes sure that nothing going wrong with this could ever affect anyhow the traffic to the slave. And the most obvious data to get when you sniff this traffic is some different kinds of top lists. And you can see here this is no, we can't. Perhaps it might be too small, but this is a top domain list for a 5-minute period, and you can see that you've got 1,500 queries during 1 minute for the domain ns.se. So apparently something is broken here. Also, if you check the top servers, and top service is top resolvers most likely, you see that it's some kind of host under 6.net has queried almost 600 times during 1 minute. And this is also very interesting, the RR types, since you can very easily see when these levels differ, you can often very easily find what kind of issue is at work here. And in the configuration files, you set thresholds that say that, for example, you should never see more than perhaps 10% of MX queries, because then something is wrong. And as you see here, this has been colored red for MX queries, because 31% MX queries against us should never happen. And also DS queries cyan, because it's too low, and NS queries 0.5% against us. That's insane. So that's blue basically. And this, of course, this is a configuration file, because for resolver operator or something, you would have very different values here. Since this is on a slave server, authoritative slave server, we should only basically see the NS, mostly NS queries or E queries. And this also, the GUI is slightly interactive, so you can dig down into data. In this instance, we have seen 5,400 queries per minute for the domain tiscali.se. Then we can double-click that one, and then we can see what servers asked about tiscali.se. And then we see here that due p2p.nu queried 5,400 times. So basically all the load against tiscali.se was due to this single server. It's very, very normal. So one server freaks out and queries a lot. And you see these other, they are still in the top list, but 1 query per minute, I mean, it's probably normal. And here again, you can also double click this server to see what did this server actually query about this many times. And then you see that he queried 5,437 times for home.discali.se in A. So yeah, something is very broken here. And yeah, man, with this tool, it takes 20 seconds to find this, and you can actually check what the problem could be, and it's most likely resolver is broken or the host is broken somehow. And other possibilities which you can use DNS2db for. More kind of top lists. I mean, domains, resolvers, query types. That's what you saw, but you can make other top lists too. Broken packets, always interesting. As it is designed today, if you get a malformed DNS packet or someone trying to hide another kind of data in a DNS packet or something, those queries are put into a separate table in the database. So those queries you can see the full query. That's very good because sometimes when a bind vulnerability or something is published, people start to abuse it and try deviations from the vulnerability and stuff, and that's very interesting to get separate and see the full packet. Deviations from patterns are also easy to see. With the top lists, it's easy to when you sort stuff, it's easy to see deviations. And yeah, queries from specific resolver, specific domain. That's when you go dig down into the data. Distribution for query types, also interesting. How many queries are over TCP, over UDP, and stuff like that. And also how many are sent over IPv6, also interesting. Origin with GeoIP, I'm not sure. I don't think that's in now, but it should be very easy. I mean, you have a database, you have IP addresses. Not hard if you want that. It's not hard to find DNSSEC enable resolves either, since you get all the flags. You can find this RD, AD bits and stuff. So it's not hard to dig down into data, since you always you log everything, and those, especially these the bits are very interesting, since when you search for something specific, that's the best part to find. So yeah, has the X-bit unset. And also after the Kaminsky bug, it was very easy for us, since we have all this data and we have databases, so it's very fast for us to go through a whole lot of data. He went through, it looks like he went through only 5 minutes. I probably did, but still, in 5 minutes, resolver will most likely send us more than one query, and then we can see the port randomness from their source port. So my friend colleague Rickard made this little script that just checked all the resolvers with the incoming queries, checked their port randomness, and got some very nice graphs. And as you can see here, it's it's quite different. Either they don't run them at all, or they run them very poorly, or they have decent randomization. And this is statistics, where he checked the top 1,000 resolvers and the top 100 resolvers. When the Kaminsky bug hit, how many were patched then, and then waited time and constantly checked to see how these were patched, because the top 100 and the top 1,000 are the biggest resolvers, or the broken ones. So they are most interesting with this kind of statistics. And as you can see, in the beginning, the top 1,000 had 80% vulnerable resolvers, and the top 100 had 60%. So that makes sense. The big ISPs perhaps have better resolvers, and in the top 1,000 there are a few broken resolvers, so they most likely have a higher percentage of broken ones. And you see over time they got patched, and here in the end it's flattened out. And I think I'm not sure if my colleague has done any more tests. This was more than a year ago, or 2 years ago. But I don't think they have gone to zero. So it's probably around 10% still out there with unpatched from the Kaminsky bug.